Buenas tardes. I'd like to start by saying thank you to Douglas Coleman for the opportunity to present this project to you all today. We're going to talk about Las Cristinas, which is a bit of an enigma of a copper property in Chihuahua. It's held by a new company we've started called Quetzal Copper. So we started trading on the stock exchange in Toronto a couple of months ago. And here's our standard disclaimer. So Quetzal has 4 properties in total. We've got 3 porphyry properties in southern British Columbia in the south central alkalic copper belt. They're all near old producing mines. But we're going to talk about Las Cristinas, which is in Chihuahua. It's about a 2-hour drive northeast of Mexico or of Chihuahua City. Very easy access. You can get there in a normal car without too much trouble. It's about 20 kilometers south of the actively producing Palomosis mine. The area is located in a known CRD district in Chihuahua. These are a bunch of prospects, old mines, current mines there that are all of CRD affinity. Cristinas itself was described in the past as a mesothermal vein deposit, which is a mainly copper mineralization, is a little bit unusual. So we had a look at it, and some of the features that I saw there kind of led me more to think that it was more of a CRD type affinity. It's hosted there in all the greenish rocks there are Cretaceous sediments. So they're part of the Chihuahua Trough. They've been covered on the west side by younger volcanics. The whole basin was accreted onto Paleo North America, so there's a lot of folding. Go forward here. A little closer look at the geology. The green rocks in the center are a series of sedimentary formations. The center one there, La Casita Formation, is the kind of early Cretaceous package that hosts our main mineralization. And the zone in particular there is kind of wedged in between 2 different felsic intrusives. The one on the bottom left is a granodiorite intrusive, and the one on the north side is a polyphase felsic intrusive. And the presence of those 2 intrusions was also part of the reason why it got me thinking about this could be related to more of a distal CRD type of a system. Looking at a cross-section of the rocks there, you can see they all dip steeply to the southwest. Turns out that they're all isoclinically folded, so there's a lot of structural deformation going on there. The formation in particular that we're hosted in La Casita is a package of limestones, shales, also some clastic sequence in it. So it's a fairly broad range of sedimentary environments. So just have a quick look through the different rock types there. This is the clastic phase. Ranges from fine sandstones to conglomerates. Some of them have been metamorphosed to quartzites. The quartzites tend to hold up the ridges. Not always, but most of the ridges in the area are quartzitic sandstone. Along trend, they may trend from sandstone into conglomerates, back into sandstones. So it's a fairly active environment there. Most of the clasts in the conglomerates are fairly angular, so it's a very proximal environment to their deposition. Locally, some of the sandstones are totally carbonate matrix, and so here we have classic Rillen-Caron weathering, more typical of karst environments, but it's actually a sandstone. Locally, the quartzites here have some pyrite in them, either coming in as possibly it was disseminated pyrite, part of the original formation, but you can also see clearly cost-cutting pyrite coming in the vein in this deposit. So we don't really understand the significance of that as yet. This is more typical of the whole region. It's interlayered fine limestones and shales, and in around the mine area, the limestones tend to be a little thicker bedded, and they're cut by these mainly bedding parallel calcite veins, which I'll describe a bit more on ahead here. This is the felsic intrusive that's on the northeast side, very felsic poor, and it has a fringe zone on the outside that has no mafic whatsoever. And another part of it is an actual rhyolite flow dome that come in. So it's a very multi-phase felsic center. This is it's not a totally completed geology map as yet, but the shows the two bounding felsites intrusives. The one on the north side was those rocks we just looked at, really mafic poor felsic intrusives. The long green trends there are the quartzite horizons. It's not clear whether there's really that many or whether they've been isoclinally folded and they're being repeated. And then some of the veins there, which we'll look a little closer at here. But on surface, this is what it looks like. The very left side is our felsic intrusion. The little valley in there is a package of mudstones in the footwall to our zone. Then the ridge there on the dactyl vein those are quartzites. And then the main host rock through the center of the photo are all those layered sediments, medium bedded. And the structures which they mined out right from surface there are visible with the holes on the hill. This is looking back the other direction to the northwest, the old mine workings there. These workings date to, we're not exactly sure, somewhere around the 1950s. They were mining the oxide coppers. They went from surface down to maybe 60 meters thereabouts. And basically they hit the water table and it turned to sulfide, and that was as far as they went. This is some of the isoclinally folded sediments that I was talking about. That's the early phase of deformation with where everything was being accreted onto North America. Then there was later strike slip along the sediments, creating some kink folds in the individual layers. And these kink folds are pretty important because they are actually cutting by the mineralizing fluids. So here we've got the mineralizing fluids coming in right along one of those kinks, and the plunge of the axial plane of that fold is where some of the ore chutes are. So if we look back at this photo again, you'll see along the trend there, so there's a couple of jogs or kinks in the mineralization, and those were the wider ore chutes. So we're starting to get a better understanding of how that's working on a bigger scale as well. During the mapping there of this is the footwall to one of the main veins, was looking up this, and it kind of struck me as being a little bit unusual. And right down there, so I took that measurement, and it agrees with the same plunge as those kink folds. And it turns out, I hadn't heard about corrugations before, but David Rise published this a couple years ago, giving a good block diagram there of what corrugations are, and basically they're large-scale slick and slides. And of course, if you've got large-scale slick and slides, you've probably got some small ones like this. So these are more your standard ones, and the same plunge shows up in those kink folds. And you might barely make out the copper oxides right there on that fault plane. So that corrugation is up on the top of that hill, the white arrow pointing down there. The slick and slides were taken at the base. So this is looking a little bit obliquely on, but straight onto the vein. You can see the red lines there are outlining one of the dilational jogs along the structure, which opened up during the strike slip movement, whereas the slick and slides were more showing normal fault movement as the mineralizing fluids were coming in. One of the things that we've picked up that hadn't really been noted before was these hanging wall splays, the yellow dashed lines. They're not all that wide on surface as yet, 10 to 20 meters or centimeters, sorry. But where they're going to intersect the structures, they'll be creating ore chutes as well. A view along the main vein there, up at the level where the slick and slides were taken, and then moving back with basically the same point of view, but from down in the valley. So that's where the vein comes around, and then you can kind of see, the pointer doesn't work very well here, but after it comes down off of the ridge here, it actually turns back and gets more back onto trend. So that's the jog there, and then back along trend of the vein. Of course, it's not totally simple. We've got another set of slick and slides with a different orientation. These ones are dipping a little bit more to the southeast. So it's definitely was inactive for a long time, multiple pulses of movement and mineralization. You can see the copper oxides here on the slick and slide plains. So these are the main veins that we've got mapped to date. The kind of brighter red colors are the previous ones that were mined. The darker red ones that aren't quite as long are hanging wall splays that I picked up in the mapping. We don't have a good feel for the continuation of those so far. This is what the strike slip movement seems to be configuring on the main set of veins, creating these dilational zones in this area here. Let's see if I can get the pointer. Oops. There's kind of the dilational jog we were looking at before in the Milagros area there. There was a previous program of drilling done in 2014 by Cyprium Mining. They were hoping to be able to develop a resource on the copper oxides and reopen the mine. They only did a small program of 12 holes. Their deepest holes only went down about 80 meters. But in their intersections, they got a few good intervals, which is what caught our attention, was 2.3 meters at 3% copper. Kind of picked up our eye, and we thought, well, this might be something that's worth a look a little closer. And then this is where their deepest intersection was. This one's about 80 meters down below surface, and it's 4.3 meters at 3.2% copper. So those are pretty attractive numbers, and if they continue down at depth, that could actually amount to quite something. And the whole depth potential is completely open. Another thing of note, if you notice up on the top of hole 9 there's a little intersection up here. On this hole, it didn't grade very well, but on one of the other holes at that same upper one, it was 2% copper over almost a meter, and that's one of the hanging wall veins that hadn't been noticed before. So what does the mineralization look like on surface? It's all oxidized material, malachite, azurite, some scoriadite as well. But if you look around enough, there's chalcopyrite to be found. It comes in along some of these veins. It's coming in distinct pulses. On this example here, we've got probably more in the center part. It's just a pyrite pulse. And then the one on the outside edge there is coming in as a separate chalcopyrite pulse. So we've got multiple pulses. Some of those I took out the photos because I thought I wasn't going to have enough room here, but there's massive bladed barite in some of the veins as well as a distinct pulse as well. So this particular case is from a small bedding parallel vein that's only about almost 10 centimeters wide, but half of it's chalcopyrite. And there you can see the bedding, it's bedding conformable. And this particular location is about 600 meters away from the old mine zone and 200 meters up into the hanging wall. So the copper is definitely in the system over quite a large area, and areas like this have never been tested in the past. The main form of the veins is they're bedding parallel. And there's also a lot of splays coming off, as is shown in here. So the intersection of those two sets of veins should be creating some decent ore shoots. This one here is kind of a demonstration of the multi-pulse nature of the veining that's been going on. The early white calcite is I believe, is the calcite that was driven out of the original bed that was replaced as the original pulses of fluid came up. And it created these halo of small calcite veinlets around the main mineralized zones. Then you've got later cross-cutting pyrite-rich ones, and then cut again after that by anchorite, iron carbonate veinlets as well. And then you can also see in there of the hematite is actually replacing some of the calcite in those as well. This is one of the examples of what got me thinking along the lines of a CRD you can see the fluids are following these little fractures and then moving out from that and actually replacing the limestone. So it does have some characteristics along those lines, though I'm starting to doubt that a little bit. But this is another example of an early fracture. Mineralizing fluids have come in, and then they're actually eating out and replacing the host rock around the veins. And then post that, we've had shearing along the structure, brecciation in the hanging wall portion there, and continued pulses of mineralization coming up during those events as the regime shifts to more of a normal orientation. So this is just a simple schematic of what the veins look like there. Our two main veins are the ones on the right side, dipping steeply around 60 degrees. There's this parallel hanging wall vein that they picked up in one of the drill holes, and then which we also picked up in our geophysics, which I'm coming to. And apart from those main veins that are bedding conformable, we've got these cross-cutting hanging wall splays, which are likely to turn into something fairly significant at depth as well. So a couple of years ago, before we optioned the property, we did a program of this to determine whether there really was some good depth potential to these veins. So we knew we had good oxide mineralization, didn't know whether it might be supergene enriched or not. We wanted to know is there some depth to these, and the depth of the detection limit on this is about 350 meters. Very strong conductors. They corresponded very well with the known mineralized veins. The Quetzal vein on the lower right is perfectly conformable with their previous drilling, and you'll notice how the plate actually stops just before the drill holes. This is that cluster of kind of blue lines up on the very top right are the old drill holes, and that's the oxide material, so that's why the plate doesn't go up that high. And then the greenish one is a plate that hadn't been detected before, but when we looked back at the old drilling results, they clipped it in hole 7, and they had 2% copper over almost a meter width there. So we've got some good depth potential here. We got other things up in the hanging wall that haven't been tested at all, and well, none of the depth potential has been tested by drilling. So we have some good hopes based on our neighbor to the north that these things do continue a good ways down at depth. These guys have mined down 900 meters along the same stratigraphy in ore the whole way. But you can also see in this the structural preparation that's created ore lenses. You have a fatter one there, a fatter one at the bottom, and then a kind of a thin zone in the middle here. There's clearly some strong structural control going on these as well. So as I mentioned, it's got some characteristics of CRD, but some other ones of just the fact that it's copper being distal doesn't really work very well in the CRD model. So one of the things that we've recently come across that might be a better explanation for this style of mineralization is actually from Southeast Australia. The Lachlan Fold Belt could be a fairly good analogy to the Chihuahua Trough sediments. They've been very actively compressed over time, and as the basin inverted, created a lot of structural plumbing. In this case, the CSA mine is mining copper and silver, which is the same mineralization that we've got, and they've been followed that down, and they've mined it over 1,200 meters down dip. So I think either way, whichever system it might be, there's certainly some really good depth potential to be had there. So the next slide, this is where I'll need them to start my little video, just a little flyby of the 3D model of our system. This was prepared by Abraham Lopez. He flew a drone survey for us to get a detailed topographic survey. Ustedes necesitan iniciar el video, por favor. Here we go. So we're just kind of moving down in there. You can see the mined out portions on surface. And as the topography rotates there, you'll be able to see the underground mine workings. He was able to scan these using LiDAR on his cell phone. and then put them into 3D space and connected with the surface topography. And then next he was able to build a 3D model in Leapfrog of the veins that are already known. We used the surface data, and then you'll see the red circles there where he was able to take strike and dip measurements actually in the underground workings to give us a little bit more control on the vein model. And then we'll just kind of zoom back out and come back up to surface. So we're getting ready to start a drill program ourselves. Hopefully in a few weeks we'll be up and running to be able to start adding some new data to this. And one of the first things we're going to do with the first 2 drill holes is to do some downhole EM to get a little better resolution on the plates that we have and to get a better depth potential of what we're looking at to be able to help plan our drill holes a little bit better. So hopefully next year I'll be able to give an update on this with some better depth results and be able to say it's actually going to be a discovery. So aside from this one, if anyone's got any copper projects that they're looking to option out, we're interested in looking for those as well. I think that about covers it. If anyone has any questions, I think I'm probably under my time limit, so. Steve?
Yeah, if I understood you right, you're talking about the stratigraphic section dipping to the southwest. And in these diagrams, is there closure to these folds? I mean, they're tilted up pretty steeply so they then come back around at some point.
I'll forget the first one. But.
Whether it's a CRD or a mesothermal vein of some kind, what do you think's driving? Is there a suspect intrusion? I assume you're a magmatist.
The possible intrusions were those bracketing felsic intrusives, granodiorite on the southwest and polyphase 1 on the northeast. So either one of those could generate skarn-style, CRD-style environment. Yeah, there is skarn alteration on the southwest one. So that is a possibility. As to the structural repetitivity, we haven't done enough mapping to really have a good feel for that, but I'm pretty sure that some of those quartzite beds in particular they're coming back up and being repeated. So the whole sequence has really been squished. Afuera de nuestros lotes hay, es típico de skarn, va de hornfells, mármol, granates, todo el suite de típico de skarn de alteración, pero no es en el área de mineralización. En el pasado han hablado de algo de, creo que fue clorita, como un halo de la mineralización. Yo no lo vi en superficie. Vi que las calizas están tal vez cristalizado o tal vez es clorita muy fino. Yo no lo vi bien. Espero en los barrenos va a estar poco más claro esto. Y si es cierto, va a cuadrar mejor con el estilo de Cobar de Australia porque el estilo de alteración de ahí es clorita. Si hay buenos leyes de plata, nada de manganeso, tiene barita, tiene arsénico, tiene cobalto. Pues muchas gracias.
Thank you.